which LED do you predict will be brighter? The LED in circuit 2 or the LED in circuit 4? Pause while you answer that. How are these circuits different? Everything about the circuits are the same except that circuit 4 has a 10K resistor in parallel across the LED, and that's not there in circuit 2. So how does the presence of that 10K resistor affect the brightness of the LED in circuit 4 compared to circuit 2? Whenever we want to compare two circuits and one of them is in parallel or has a parallel section to it, we need to first simplify the parallel section and replace it with an equivalent resistance. So we want to replace this parallel section with one resistor which has resistance equivalent to that section. Now, we cannot do that mathematically because we don't know the actual value of the resistance of this LED. So we can't use a formula to help us with this right now. But we can just reason through, because we know that when we add resistors in parallel, that decreases total resistance. In other words, if we were to take the LED as having resistance R like that, the size of the R is meant to indicate the size of the resistance. So if we have those two LEDs having the same resistance as one another, to simplify matters, let's take it like that. Now we want to compare this section, this whole parallel section, to the value of the R shown there. In other words, what does adding the 10K do to the total resistance of that part of the circuit? And we know that adding resistors in parallel decreases equivalent or effective or total resistance, so that the effective or equivalent resistance of that section now must be less than the R that we showed before, the R of the LED. It's like when you have two pipes in parallel. The combined resistance of the two pipes in parallel is easier. It's less resistant than any of the individual pipes, because adding pipes in parallel makes the overall effect easier, like a thicker overall pipe, lower resistance. So whatever this resistance here of the equivalent resistance is, it is less than the resistance of an LED, because adding resistors in parallel always makes the equivalent resistance lower than the least resistant component. So we can replace this parallel section with a single resistance which has less resistance than either the 10K or the LED. There we have it. So now we are comparing two circuits which are both series circuits. So it's much easier to think about them because they are both series circuits. In both cases, there is 9 volts supplied by the battery, and that must be shared between the two components in the circuit. So let's make 9 volt be this size. The size of the letter is indicating the quantity. So those two are meant to be the same size. I hope they are. And so the potential difference across the 22K plus that across the LED must add up to whatever it is, well, 9 volt. And the potential difference across this 22K and the equivalent resistor in circuit 4, the sum of them must equal 9 volt as well. So how is this potential going to be shared? In both cases, we have 9 volt that must be shared between two resistors. How is it going to be shared? The voltage is shared in the same ratio as the resistors ratio. So here we have a 22K resistor, and here we also have a 22K resistor. So that is common between the two circuits. We don't know the value of the LED's resistance, so I can't actually write this R the right size, but let's just say it's like this. In circuit 4, the equivalent resistor has less resistance. Sure, I really have to write that R very small. Less resistance than the resistance of an LED. So can you see that the ratio between the two resistors lies more heavily in the favor of the 22K resistor in circuit 4 than it does in circuit 2. So circuit 4's 22K is going to take more of the voltage than what circuit 1's 22K takes, leaving less voltage, because the sum must still equal 9 volt, than what is left for the LED in circuit 2. Put another way, the LED here is greedier in comparison than this resistor is. So it must get more voltage than what this resistor takes, since they are both with a 22K resistor. Now we're only interested in the LEDs themselves, so I've removed the other information. Now let's think about the current strength. Now, comparing the current strength through circuit 2 and circuit 4 equivalent is not very helpful. Why? We'll see why just now, but let's first just do our reasoning concerning current strength. So we can see that circuit 2 has a higher total resistance because it's 22K plus whatever the resistance of the LED is. That's higher than circuit 4's resistance because circuit 4's resistance is also 22K but added to something less than an LED. So the answer must then be less than in the case of circuit 2. And so the current strength through circuit 2 must be lower than through circuit 4 because circuit 4 is an easier circuit than circuit 2 is. However, if we look back and compare the actual circuits, not the equivalent circuits, yes, we've seen that the current strength in the main part of the circuit here, circuit 4, will be greater than through the main part of the circuit in circuit 2. But the current splits into two, and only some of it travels through the LED in circuit 4. And we can't know in what ratio they split. So current is not very helpful in telling us much about the power, because the power dissipated through the LED is related to the current strength through the LED, not the current strength in the main part of the circuit. However, after we've done the reasoning about potential difference, then current strength does become clear and useful. Why? We've already seen that the potential difference across this parallel combination must be less than across this LED. Why? Because the rest of the circuit is the same, but the LED is greedier on its own than when in parallel with a 10K, because adding resistors in parallel decreases resistance. So the greedier setup is when the LED is alone, so it takes more of the voltage supplied. Now the potential difference across the parallel section is the same across the LED as across the 10K resistor. So we can see that in circuit 2 there's quite a strong potential difference pushing current through the LED, but in circuit 4 there's a low potential difference pushing current through the LED, even though in both cases they are LEDs. So if we just look at them, not the parallel combination, just the LED, focusing only on the LED, their resistances we can say is the same, and so the current strength through circuit 2's LED must be more than through circuit 4's LED, because for the same resistance there's a greater potential difference across the LED in circuit 2 than in circuit 4. Power is equal to V times I. Circuit 2, we have a big number of V multiplied by a big number of I. We're going to get a bigger power, a greater power, more power dissipated than in circuit 4 through the LED. So the LED will shine brighter in circuit 2 than what it will in circuit 4. So let's now compare circuit 2 with circuit 4. We see the brightness of the LED there, and compare that with the brightness of circuit 4's LED. Can you see that circuit 4's LED is very dim? Circuit 2's LED is brighter than circuit 4's. That means that circuit 4 has a lower power dissipated through the LED than circuit 2.